The next topic we're going to be learning about in chemistry are gases and how they behave. So before we get into that, we need to talk a little bit about exactly what gases are and pressure with gases. As you remember from your states of matter, there are solid, liquid, gases, and plasma. So what do we already know about gases? We know that gases have no defined shape and no defined volume, right? So they take the shape of whatever container they're in and they fill up the space of whatever container that they are in. There's some other things, however, that you need to know about gases. Um, Gases can be easily compressed, okay? This is because, remember how the particles are so spread out in a gas? Well, you can squish them together because they're really spread apart, okay? And as we see our little balloon monkey, that's why they make such great balloon animals, right? You can put them in a balloon, you can twist it, you can compress it, you can squeeze that air, and so gases are really flexible in that way. Gases also mix completely with other gases. So if you think about the air around us, like we've talked about when we were classifying matter, the air around us is not one thing, it's many things. It's oxygen, it's nitrogen, it's carbon dioxide, there's some argon in there, there's some radon maybe in the air. So there's lots of different gases, but they mix together, and this would be a homogeneous mixture because it all looks the same throughout, right? And then gases also exert a pressure on their surroundings. And this is weird to think about, but basically the air around you is pushing on your skin at all times. And usually we don't feel it because we've been living with it our whole lives, so our bodies are just adjusted to it. But if you think obviously something like wind, that's when you can feel it more strongly. But there's always pressure being exerted by the atmosphere around us. Some other things that we're going to just kind of say to be true as we're talking about gases is that gases are made of particles, and that the volume of the particles is zero. Now, that's not exactly correct because gases are matter, which they have mass and volume, but basically the particles are so small and they take up so little space that we can kind of just ignore it, okay? The particles are in constant motion. As we know, everything is always in constant motion, and these particles collide. They hit each other, they bounce off walls, they hit surfaces, and that's what causes that pressure, okay, are these collisions and the bouncing. Um, the gas particles don't attract other gas particles, they don't repel other gas particles. Now, this is a pretty simplistic view, and technically some do, but for our intents and purposes, we're going to say, hey, there's no opposites attracting, there's no likes repelling here, they're just not interacting in that way. The last thing we're going to assume about gases is that their kinetic energy is proportional to their temperature in Kelvin. So if you remember, temperature is the measure of something's kinetic energy it has. And the whole kind of point of degrees Kelvin is it literally is the measurement of the kinetic energy that the thing has. So that's why scientists use that temperature scale. So when we're talking about a gaseous pressure, we're looking at what are all of the collisions happening between those particles and all the surfaces, and that's that gaseous pressure. This word here, simultaneous, that means they're happening at the same time, right? So if you think about all of the collisions that are happening right now between the gas in like the room you're sitting in, between your skin, between the other gas particles, between the walls, that would be the pressure that the gas is exerting. So as it turns out, there's a pretty simple way to measure gas pressure, and it is using a barometer. Maybe you've heard about this because on the weather, they'll often sometimes report what the barometer is doing. The barometer is a really simple device. It was invented in 1643 by this handsome young chap. He's an Italian scientist named Evangelista Torricelli. And so here is what a barometer looks like. Okay, so basically what he did is he took a tube and he filled it with mercury. Mercury's chemical symbol is Hg. And there was a dish with mercury. And he took the tube and he turned it upside down and plopped it in the dish. And what happened is, boop, some of the mercury came out into the dish, but not all of it. It stopped. Why did it stop? Because see this atmospheric pressure. The air was pushing down on the surface of this mercury, and so the air stopped it from dropping any further. Okay, and so basically, depending on what the air pressure is, this level can go down or this level can go up, depending on how much the air is pushing down on this kind of puddle of mercury here. And so that's what a barometer does. And so this 760 millimeters is equal to 1 atmosphere. What does that mean? 1 atmosphere is roughly what it's like to be at sea level, which is where Madison is. So basically, this is the amount of air pressure we're feeling. If we had a barometer, it would be somewhere close to this value, maybe not perfectly that, right? But it'd be somewhere close to this. The height of this mercury would be about 760 millimeters, which is about 3/4 of a meter, just in case you were wondering. So as you can see down here, we have lots of different ways to measure atmospheric pressure. One is in milligrams of mercury because barometers can use mercury. One is in torr, T-O-R-R. That's a unit named after the inventor of the barometer. So 760 millimeters of mercury is equal to 760 torr, which is also equal to 1 atmosphere. So that's what we say, hey, at roughly sea level, we're just going to call it 1. Just going to say it's 1 atmosphere. Okay, so all these values are equal. And then oftentimes in science, scientists around the world use units called pascals or kilopascals, kilo meaning 1,000. And so 1 atmosphere and 760 torr and 760 millimeters of mercury is also equal to 101.3 kilopascals. I don't want you to stress about that right now, but just in case in the future you see these pascals, now you'll kind of know where it's coming from. So pressure is not going to be constant. Pressure can be changing. And what could change the pressure? The two main things, at least around us, that can change our pressure every day would be your altitude. Now, here in Madison, we're not really changing our altitude very much. But if you were to feel the air pressure here and then go to Denver, Colorado, let's say, that is, they call it the Mile City because it's mile high, right? So it is literally a mile up in the air with the mountains. If you were to go to the top of mountains, like in Denver, there's less air above you because you're higher up. So there's less air between you and space. And so there's less pressure on you. And so oftentimes people have a hard time breathing up there because they feel like the air is, quote, thin because there's less of it up there than there is compared to us here at sea level. And then even if you would go to the bottom of a really, really deep canyon, there would be more air above you between you and space. And so there'd be more air pressing down on you. So you'd feel more air pressure. The other thing that can change the pressure of gases would be weather. I'm sure you guys have seen sometime in the weather how they might show a weather map like this one, and they'll say, oh, there's a high pressure front coming through, or there's a low system moving through the state bringing blah, 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 right? And so we're not really going to get into exactly how air pressure can deal with weather. If that interests you, I highly suggest taking the Earth Science class with Dr. Bob. But know that different pressures of air and coming through can kind of have different weather things happening, and that's why we see some of the weather patterns that we have. So those are some basics with air and gases and pressure. And, you know, don't worry, we're going to be talking about this more and more, and you're going to get some hands-on experience. So if it doesn't make sense to you quite yet, hopefully it'll make sense pretty soon after we do a little bit more work with gases.